Okay, on to relational data in data transformation and exploration. So lecture is going to be all about how we combine data sets together. So as we mentioned previously, it's really good practice to maintain smaller data sets and then merge them together through code. Using multiple tables of data is called relational data because we are interested in the relations between data sets, not individual ones. Relations are always built between pairs of tables, and to do this work, we need some terminology. So we have mutating joins, which adds a new variable to one data frame from matching observations in another. We have filtering joins, which filter observations from one data frame based on if they match an observation from another one. And set observations, which treats observations as if they were set elements. And so back to our pipeline here. So we're still in the transformation, and we're going to be using a lot of dplyr for this. So in this lecture, we'll use the library NYC Flights 13 from the R Data Science. You can check more out about it at the website. This is not a biological example, but it's super useful for these concepts, so bear with me for this lecture. And this library contains data on flights in and out of New York City. And we're going to be talking about 4 data sets: airlines, that describes all airlines in New York City; the airports, that describe the airports and the flights that go to and from; and then the planes, which describes each plane; and the weather at each New York City airport for each hour. And really, most of this lecture is based on the R for Data Science book and the chapter on relational data. So I give thanks to them, and please check it out if you want more information, but this work really comes from them. And so we've talked a bit about relational data when we were talking about how small data sets can link up to large data sets. And so again, here's another example, but using this NYC Flights database. And so here in this diagram, you can see that flights connects to planes via a single variable of tail number. You can see that flights also connects to airlines through the carrier variable. You can see that flights connects to airports in 2 ways via the origin and destination variable. And then finally, you can see that flights connects to weather via origin, which is the location, and the year, month, day, and hour, the time. And so we're going to come back to keys in this section. So this is the terminology used by the R for Data Science book for a variable or set of variables that connects each pair of tables. And there are 3 types of keys. There's a primary key, which uniquely identifies an observation in its own table. So here, the tail num variables in planes uniquely identifies each plane in the planes table. The foreign key, which uniquely identifies an observation in another table. So here, the tail num variable in flights appears in the flights table, where it matches each flight to a unique plane in planes. And then there's also the surrogate key. And this happens when sometimes data sets do not contain a primary key, so you have to make one. And so here, the tail num variable in flights is not a primary key because the same plane appears multiple times per day at an airport. So if you want to create a unique identifier, then you need to create this key, for example, using mutate and row number. Then this becomes your primary key. So technically, there are really only 2 types of keys: primary and foreign keys. And a primary key that corresponds to a foreign key is a relation. And this builds on that one-to-one, one-to-many, or many-to-one relationship that we mentioned previously. Okay, so let's talk about these joins. The first type is a mutating join, and that combines variables from 2 tables. This is pretty common. And so we're going to make our flights table a little bit smaller so we can better see our data. So here we're making flights 2, and now we can actually look at it. And to add the full name of the airline to flights 2, you can combine airlines and flights 2 with left join. So here we're taking our flights 2 dataset and then selecting all of it except for the origin and destination, and then left joining it with airline by carrier. And you can see this is the output. So joins, how do they work? So the R for Data Science book has some really useful diagrams to help envision joins. So we're going to go through them. And so imagine you have 2 data sets, X on the left and Y on the right, And they each have a key variable, and that's the colored columns. The following diagram shows all potential matches with a grid line. So you can see all potential matches between each variable and observation. However, the only possible matches are indicated with the colored dots. And the resulting data set demonstrates that in this case, all variables are joined, but some observations are lost. So we still have all of our columns, but we've lost some of our observations because in this case, X had a 3 and Y had a 4, and those didn't match. So those are gone. So there's several types of mutating joins. So there's inner joins, and these match pairs of observations based on equal key variables, but they lose observations without matches. So like we previously saw, when you join X and Y, inner join X and Y here, you lose your X3 and your Y3. And here is the code to do that. Outer joins are a bit different in that they also match observations based on key variables, but they don't lose those observations. And so there are 3 types of outer joins as well. A left join keeps all observations in X, a right join keeps all observations in Y, and a full join keeps all observations in X and Y. In all cases, unmatched observations are filled with an NA. So here you can see a left join, a right outer join, and a full outer join. And so there's a question about what you do with duplicate keys. Sometimes keys are not unique, and there are 2 possibilities here. One table has a duplicate key where there's a 1 to n relationship, and here X has two keys and 2 1 keys, and Y each has 1. And so when you join them, then you see that you just get all of them combined. And sometimes you have a duplicate key where both tables have duplicate keys. And this is often an error because neither table has a unique identifier, but it's good to notice this when this happens, because if it's an error and you don't have unique identifiers, you probably need to fix that. So here you can see this is happening in these 2 data frames, X and Y, with a left join. And so we should talk a little bit about defining the key column. So natural joins, occurs when you do by equals null, and that uses all variables that are in both tables. So in our example, flights and weather have year, month, day, hour, and origin in common. And so when you do a left join between flights 2 and weather, and you don't specify your by, it just links them all together, and that saves a lot of headache. You can also join by a character vector, and that's when you have by equals X in quotes. So try joining flights and planes by tail num. Here you can see that both data sets had a year column before you joined them, but those years were different values. So the resulting variables are year.x and year.y. And so this last one is actually really useful. It's when you use a named character vector. So for example, when you specify by as the concatenation of A and B in quotes, and this allows you to match, not math, variable A in table X to variable B in table Y. And note that the variables from X will always be used in the output as the name. So here you can see that we're left joining flights and airports by destination from flights and FAA from airports. And in our resulting data frame, you can see that destination still remains. But that was the FAA column from airports. And so then the second type of join is a filtering join. And filtering joins only affect observations, not variables. So remember, those are rows, not columns. And so we've got 2 types of those. We have semi-joins that keeps observations in X with a match in Y. So here you can see that X1 and Y1 match and X2 and Y2 match, but X3 and Y3 don't. And so what you're left with is X1, X2. And then antijoins drop observations in X with a match in Y. So here we have left only that X3 column. And so a little bit about semi-joins. So say you have a table of the top destinations. I've made it under the hood. It's called top dest. And you want to know what flights go to those destinations. So you can create a data frame called trips where you semi-join flights and top destinations. And this is joining by dest. And here you can see the result. Those are all of the entries in both. And an anti-join is really useful when you're trying to figure out mismatches to see if you have any mistakes or just mismatches. So say you want to know the flights that do not have a match in planes. So here you can do the anti-join between flights and planes by the tail num, and then you get your set of mismatches. And so the final type of relational function we want to talk about are set operations. And you may use these less frequently, but they're often good for data cleaning, especially set diff. And so set operations work with complete rows and compare the values of each variable. So for set operations, it is assumed that x and y have the same variables and treat all observations as sets. So you could look at, there's three functions you might use. Intersect of x and y returns only observations in both x and y. You have union of x and y, which returns unique observations in x and y. And then your set diff xy, which returns observations in x but not y. So again, that's useful for data cleaning. And so say you have two data sets, df and d2, df1 and df2. Here are all of those types of set operations and your resulting output.